except now you make a penalty, and you end up with a really good, small, very robust tree. Okay? That's one example of an embedded method. And I'll tell you about others perhaps already next time. But I want to start, because I want to start on something. And what I want to start on today, now, I don't think we'll get very far, because I also want to show you a little bit more on preparation for tomorrow on Jupyter Notebooks. But I would like to start on a completely different type of classifier, and that's on neural networks. So before we do that, are there any questions about anything we've covered today? Nope? Oh, I think some of you already asked me questions in between stuff. So that's OK. As long as everybody understands where we are, no questions, we can go to another classifier. OK. Well, in that case, let's go to neural networks. Now, first of all, one thing to be noted is that these guys are not real neural networks, right? Real ones are inside of our brains or brains of other mammals, right? But why are they called neural networks? Why? Because they are loosely inspired by the ones which we have in our brain. Now the connection is very, very loose, and I'll tell you why. So these are nothing but mathematical structures, right? So they're not, they're not the same. It's just that the word artificial is meant to encourage you to remember that. OK, now you already heard I think a few already introductions in some of the talks, so I don't think I have to go and repeat that. But I think it's academic and prudent to actually go and go through this one more time. OK? So it's good if you hear something. If you hear it again, it's not going to hurt you. It's only going to make it better. So what are these guys? Now in our brains, right, we have neurons, right? You have this information, these electrical signals are going from they're firing, all over the place. And you have a network of these guys, right? And the connections between them, you have these synapses, right? So this is basically where the analogy comes from. These models, by the way, this is a very simple one. This is not a deep neural network. It's just a neural network. Something even called perceptron, let's say, if you have just one of these layers. So what do you have? You have the basic unit. The basic unit of a neural network is a neuron, right? It's a node. It's one of these spheres, right? And you can have 3 types. Well, actually 4 types. So one of them, obviously you have the input one, right? So that's where the data comes in, right? It could be some variable. It could be some measurement. It could be a pixel. It could be whatever it is, right? This is the input neuron. And then there you start having other neurons. And here you have what is called a layer. So they're usually in a structure of layers. At first, let's just talk about the simplest variety of neural networks, and it's called a fully connected network, where everything's connected to everything. A little bit later, we're going to talk about different variations of neural networks that are not like that. But let's first cover the very basics. Okay? So in a fully connected network, everything is connected to everything, right? Now, so each one of these you can think about as a neuron, right? So he is some kind of like a transformation hub, right? So data is going to come in, kind of like a train station, right? You're going to get a train coming in your station, and then it's going to send it out, right? The only thing is it's going to send it out a little different than what came in, right? You're going to load it up with stuff, transform it, and send it further, right? So you can think of these guys as processing units, okay? Neurons. Now, the connections between them, these are the so-called synapses, right? These are the weights. These are the things that you can tune, change. The algorithm can tune them. These are the things that are adaptable. They can change. The neurons, it cannot change. Okay, they're just going to transfer the stuff based on the rules that you told it to, right? And but these weights that connect them, that can change. It's important. They're adaptive. So here you have a layer. Let's say only one layer, called a hidden layer, for historical reasons. You could have more than one layer. You could have 10 of them, 50, 100, billion, infinity. Do you need that many? There's a theorem that says you can actually learn any function if you only have 10. That's why you have the word activation function, transfer function. So basically what you're doing is you're going to apply some kind of transformation on the information that comes into each neuron. And that is going to be some function. And the functions can be different. It could be a sigmoid, right? It could be a ReLU. I'll tell you what all those are. You already heard the names, I think, a few times. But in the 90s, this was the guy, sigmoid or hyperbolic tangent. Very, very similar function, right? People liked it because it worked. Remember what I told you yesterday? Just because something works doesn't mean it doesn't mean it's going to stay around forever and people won't find something better. Well, this guy ended up introducing some problems that people ignored for a while until they couldn't ignore it anymore. And that's why nobody really uses them now, because people found that there are other activation functions that work better. But it took a lot of trial and error to get there. And I can tell you that 99% of the field was using them, just because other people have used them and it works. So just keep that in mind again. But for now, let's just assume that's the form that works. The nice thing about it is that, you can differentiate it. And actually, there are some interesting properties that have to do with differentiation, which cause some problems. And I'll tell you what they are. Now, the point is that a function like this is going to take an input and then transfer it somewhere else, give you some other value, right? So all you're doing is you end up with a function. This whole thing, all it is just a mathematical function, right? Just a bunch of mathematical operations, right? Addition, multiplication, so. Or sometimes, you transform it to some exponent. So what you have here is inputs come in, multiply them by the weights, you get here, and here you get some sort of transformation. So here, let's say, are the original inputs. So here is the xi, right? Then on top of them, you have dji. You sum them over. You add this bias term, which is just like a constant, right? Why do you need that? Anybody want to guess why you need that? Yeah? Nope. Another guess? Anyone? All right. Remember, these guys here are mostly normalized, right? 0 to 1. So what that means is that if you're living within 0 to 1 or -1 to 1, within some pretty wide interval, you're not going to be able to get out of that, right? Let's say you're dealing with estimating continuous functions, and your range is, I don't know, -1,000,000 to +1,000,000. How are you ever going to get there? You're never going to get there. So in some ways, one of the reasons for it, and that's not the only reason, but one of the reasons that it also helps you change scales without actually modifying the weights. You don't have to introduce some crazy weights to get up to those scales. That's one of the reasons. But there is other reasons. That's why it's also called a bias, because you do need to actually keep this bias term. But it's a constant that you have. Then you transform this thing in some way, let's say hyperbolic tangent or sigmoid or ReLU, whatever it is. And then, again, you end up with another weight connecting this to the output. The output, now that depends. Depends what you're going to use it for. If you're going to use it for regression, which is a continuous function estimation, then you use it as it is, right? You have this function, right? And then if you want to use it as classification, then now you end up with two outputs. Then you want to discretize the thing, and you end up being between either some 0 or 1, -1 or 1, whatever. So that's really all it is. But what we talked about so far is kind of how it works. How do you process it once you've trained it, right? We didn't talk about anything about how do you train the thing, right? Kind of like when we talked about the tree looks like this. We talked about how to use it. We didn't talk about how to build it. For now, we haven't talked about how to train this guy. We just talked about his structure. Now, are there any questions about the structure? Pretty clear? Okay. Now remember, these things can go layers and layers and layers. They can go very deep, very wide, all sorts of things. Well, you may ask, well, why deep? Why deep learning? Why not just wide learning? Why? There's a theorem that says if you go wide enough, right? Well, it all has to do with complexity. For those of you who've studied computer science, you know that algorithms have complexity. And you actually care about how long each algorithm takes, how well it scales, how well it scales with, the number of inputs. And it turns out, okay, that the wider you go, right, it doesn't scale in the same way. Sorry, I mean, the deeper you go, right, the deeper you go, the longer it's going to take. So it turns out that you can sometimes take a little shortcut and find, something that's not necessarily as wide, but rather than that, you're gonna get some pretty good performance just by going kind of deeper rather than wider. So it's a shortcut, basically. It's a computational shortcut rather than anything else. But in principle, you could learn any function you want, anything that you want, with just a sufficiently wide, by sufficiently, it could be really, really wide network. And you also don't know how wide or how exactly. So you have to find it. Okay. Now, here's the key point, and I think I'm just going to try to convey to you this idea, and then maybe we'll look at some other things. But the important thing is, how do you train this dragon? Okay, the way you train this dragon is, you've already heard this term, I think, a few times today, yesterday. It's called back propagation. Right? What does it mean? It means you're propagating something backward. Right? What does it mean? That means, so when you compute a network, you go from left to right, just like you read. Right? Inputs go in, compute stuff, look at the output. Now, suppose you do it once, you look at the output, and then you can compare it with the output you expect. Right? Let's say if you're doing regression or classification, and then you can see how well you're doing. You can assess something called the loss. Right? You can figure out how well am I doing at this point. And then you can say, okay, well, I guess I'm not doing perfectly. There's some errors over here. So let me actually go back. Let me go back, right? And let me then start changing my weights, based on, the way the errors are, the way the errors are sort of moving. You kind of go and you do, something called gradient descent, right? You try to find sort of like this optimal path to lower your errors, right? So in the end, what you're doing is taking a bunch of derivatives, right, of these, these weights with respect to the errors, and then you go in that direction, right? You try to follow that path. You try to find that sort of way down the mountain into the valley, right? And the idea is that you go ahead and you do this, and you do it iteratively, right? So in neural networks, in training neural networks, you have something called an epoch. An epoch is when you pass things, one way and backwards, and then you do it iteration after iteration, and with each iteration, you modify the weights, and you go and you try to reduce the error, and then eventually, your error goes down, and you end up with a trained classifier. So the point is, the inputs go forward, the errors go backward. Right? Now, just think about this for a sec. This is a really important part. Right? The idea is that you compare the output of your model, you look at how well it does, and then you change the parameters of the model, kind of like in the classic regression case, right? The same idea applies here. But how you do it is a little different. So here, you can actually go ahead and, and look at how the error changes, right? If you change, if you change those parameters, right? And you kind of start to go in that direction. So that's the idea. So you look at the error gradient, right? That means derivative. It's basically like freshman calculus. You just take a bunch of derivatives. Okay, so that's basically what you're doing. So you take this network, you train it, you adjust these parameters, and you end up with some function. And that's going to be your classifier, right? And if you want to be real fancy, you can build a bunch of these and make an ensemble of these, right? Now, you may wonder, like, what, is this the big idea, right? Well, this is the idea. The way I would draw this is what you would see maybe in the neural networks of the 90s, okay? The early 2000s. This right here has a problem, okay? It has a few problems, but one of the problems that it had, I should say, is a problem called the vanishing gradient problem. As you can guess by the name, it means something's disappearing. And what's disappearing? Gradients are disappearing. So what that means is, if you decided to go deep, people in the 90s also wanted to go deep. They thought, oh, let's go deep. Let's go whatever my computer can allow me to. Sure, having 1,000,000 times more computing today helps too. But let's say at those days, they also could have done, maybe not as deep as now, but they could have gone deeper. But it didn't work. Why didn't it work? The reason it did not work as well is because when you took derivatives, remember, these are small numbers. Numbers close to 1 or less than 1. Let's say less than 1. What happens to a number that's less than 1 if you multiply it by another number that's less than 1. It's going to get smaller. Imagine doing that 4 times. Are you going to end up with anything? No. It's just going to go to 0. So what happened was, even though they were constructing these wide networks, right? By the time they took derivatives and after the second time or the third time, they would go to 0. You're not learning anything anymore. So that was a vanishing gradient problem. That had to be solved. And the reason for it was actually connected to the shape of this function, or more specifically, the derivative of this function. So we'll talk more about that tomorrow. I don't want to overload you with things. So we have maybe another 25 minutes or so. So what I want to do is just to give you also a small introduction to Jupyter Notebooks, which we're going to use tomorrow, so we don't have to waste time on that tomorrow. And it's pretty basic, so that shouldn't take me very long. And then I'll just open up for questions, and then we'll resume tomorrow, and we'll look into more in-depth into these. But I do want to leave you with the idea already today, so that at least you have some mathematical foundation for it. Now we can come back tomorrow. You can think about it between today and tomorrow and ask me anything you want. And we'll look at that. Any questions? Yep. OK. But just think of these. These are the neural networks, let's say, of pre-deep learning revolution. Now, that doesn't mean that the ones today are drastically different from this. But there are some small things that have changed. And I'll point out exactly what they are tomorrow. Yeah. OK. So let's go back to Swan. And now we can actually now maybe let me first do it. Maybe just watch me, and then you can try it. The reason for it is there is a simultaneous tutorial happening somewhere else in the world. Okay, and which potentially may or may not interfere if all of us do it at the same time. But we can try it anyway. So Swan, the idea of Swan is not to just give you a terminal. Don't get that idea. That was just a fun thing for us. The idea is to use Jupyter Notebooks. Now, if you remember what these guys are, so if I go to like the CERN box, something or another. CERN box, by the way, is a CERN version of Dropbox. That's all it is. Except it has 1 terabyte, or maybe 2 terabytes of space. So it's a little bigger. So instead of going to C50, I'm going to go to this tutorial unum. OK. Now, don't all do this at once, because I understood our bandwidth is limited. So anyway, so you can see a couple things, right? You see folders, right? You see folders. And then you see these little book things, right? These book things are called, they all have extensions IPyNB. So they are IPython notebooks, right? So there's something called IPython, which is a fancy little thing, which was invented a few years ago. And these are Jupyter Notebooks. Now, what exactly is Jupyter, right? Jupyter, as you heard somebody say, I was the other day, that is the greatest thing on earth. The name itself is nothing to do with planets. It combines programming languages. Okay, so Ju is for you have Julia, Python and R, right? That's the idea. But the reality is now it actually supports a bunch of other languages. So it's not limited to these 3. You could have C++, you could have Boolean, whatever you want. So here, each one of these is a notebook. So let me open one up. So you see some of them are called TMVA. That's a toolkit, one of the toolkits, some which is built for by some of the particle physicists. But anyway, let me open up one of them just for fun. This one. Right now, don't worry about anything that it does. Forget about any content inside. What we're going to just talk about is the structure and how do you work with this. Okay. So now I've opened the notebook. You can see that you have a bunch of buttons over here. You can save it. You can edit, cut, paste. Here you have something that runs. You can click this thing so it can run, stop, whatnot. On the top here, you can see what type of a language is used. So this one's a C++ one. Could be a Python one. Could be something else. Could be another one. So just, I opened a random one. This one's root C++. So the structure of these guys is cells. And you have different types of cells, right? It's kind of like, you know, if you ever played with like MATLAB or Mathematica or something like that. It's more like an interactive thing, right? Here, a cell can be of different types. It can be a markdown, meaning you can actually put text and pictures, you see, like this. And then you can go and edit it. I can go and edit it and say, whatever, hello. And then Shift-Enter, see? And then it's going to be just like a visual thing, right? It can be just text, pictures. And then there's also code, right? So right here, you can have code, right? Now, you know, and that's going to give you some output with response to your input. So that's the basic idea. So you can go interactively, you can put notes, you can get pictures. So it's the whole thing at once. Code, markdown, everything else. So you have something called a kernel. Now, I like to do something usually. The very first thing I do is usually restart and clear output because I don't want to, you know, for there to be any output. Note that sometimes, for reasons beyond my understanding, kernels can die. You're going to get an error saying the thing died. Just reload it. It works. It'll work the next time. Sometimes it'll work. Sometimes it won't. It's just the nature of this. See, it says kernel ready. So you want to wait until that shows up. That's good. That's good. So now you can actually execute the thing. You see, now this is a cell. This is an actual, like a code cell, right? So here, this is C++, so whatever. But it could have been in Python. But here, it's going to be empty. It means you haven't run this yet, right? If you're going to run it, while it's thinking, there's going to be like a little thinking star. When it completes, there's going to be a number. Very easy, so you can see. Here, let's say we're just going to, you know, execute some code, whatever code. It's here, Shift, Enter. Now it's thinking, and now it's done. Okay, so if you see a number, it means it's done. Okay. Sometimes there will be an output. If there's any output to be had, you will see it. If there isn't, it won't be there. So anyway, so these are like little examples, and then we'll use that tomorrow. And you can see that in your box, you have actually a whole bunch of different ones. So, and if you go back here, you'll see that this one has a little green color. It means it's running. You can kill it. You can stop it. You can save it. You can make a clone of it. Do anything you want. So you can share it with others. The only thing you can't really do is simultaneously work on the same one. So what you're working on is kind of like your own copy of it, right? So, so tomorrow we're going to look at all sorts of different examples. And I'll give you actually a couple of different options for tutorials. You'll have a choice tomorrow. You'll be able to figure out if you want to use different types of tools. You can try TMVA. You can try Keras. Try something else. So I'll give you some options. And that means you'll be working with also different types of data. You can choose to work with images. You can choose to work with, you know, I don't know, numbers, meaning, you know, data from you know, in different formats. And you can work with, you know, fully connected networks. You know, you can work with trees. You can work with anything you want. So we'll have that tomorrow. OK, so that's basically what it is. I would encourage you to just like try some notebook without focusing on the content, but just to see whether you can figure your way around a notebook. Like what I would do is maybe open the same one I just opened and see whether you can, you know, change the text in the text ones. See if you can actually execute. Remember, Shift-Enter. Execute a few of them. See if you can get some output. Don't worry about what it does today. We'll worry about that tomorrow. But just get familiar with that. So, and the really neat thing is all you really need for these guys is a browser. So, but that means that all the software that you need for it is already on this. For example, like Swan has all of that there, whether it's root or Keras. If you want to run these things on your own computer, then you need to install this software. So it's not complicated, but you have to do it. So if you want Keras, you have to install Python and TensorFlow or whatever it is you're going to run. So we already have that prepared so that you wouldn't spend, I don't know, an hour of your time or more configuring your stuff. But if you want to do things locally and you want to do things later, you may want to invest some time into that too. Yeah. OK. So I think we're going to have a little free time. You can either play with these or you can ask me questions, and then we'll resume tomorrow. Yeah. How far what? Sorry?
In terms of accuracy.
Oh, in terms of, okay, a good question. So a question is, how far, in terms of accuracy are, were you asking about deep neural networks or shallow neural networks? A different question. So if you talk about shallow neural networks performance compared to like boosted decision trees or whatever else, pretty comparable. Oftentimes boosted decision trees used to win. However, the reason it's a deep learning revolution is because some variants of deep learning algorithms have surpassed in performance all the other algorithms. So currently, it's like the leading horse in the race. But keep in mind, for a while it wasn't. For a while, people actually went away from neural networks because there were some issues. The stubborn ones didn't. They are the ones who kind of, ended up being the fathers of this deep learning revolution, right? But the point is that right now there is a difference in performance in some cases. You cannot always guarantee that, but yeah. But nowadays it pays to learn these algorithms. So yeah. Anyway. Oh, one thing I should talk about maybe today is data formats, right? Let me just briefly mention that, right? Now, you will hear about different formats, right? You'll hear about in different contexts, right? So in particle physics, we happen to like our own things. So particle physicists have developed their own data format, which is useful for particle physics, called root. Now, there's also a whole software framework called root. Now, that's not the same. The format itself is something extremely optimized. It's super, super optimized in many different ways. It's good. But the framework that comes with it is a huge behemoth of stuff. Not everybody likes it. But the format itself that it uses to, and we use it for data, to collect data, to share data, all sorts of stuff, to do analysis with. It's a really optimized format. But it's also quite specific to particle physics. There are other formats that people use outside in the industry. It's HDF5 and others. There's a whole zoo of them. So important to note that each different tool likes its own different format, right? Some of them take other tools' formats, so there's some commonality here. But in the end, it's just a representation of data, and there is plenty of converters around. So don't worry if you don't know some format or know some other one. Just know there's converters. You can convert your data between one and another. It's not a problem. So don't worry. With Python tools, sometimes you have to learn pandas and data frames and things like that, and they're pretty easy things. So don't worry. You can always take things from one format to another. So don't worry if you've dealt with one of them. And that's actually where a lot of the recent efforts have gone into, is actually building these sort of ferries and bridges and ways to convert formats from one to another. But the ones we're going to talk about here is going to be HT5 format and root, which is something that we use ourselves. Now, root is basically just a tree, right? It's basically like a tree, and the data is stored in kind of a tree. So, and you have leaves, and then you have kind of like an easy way to express things that are multidimensional. So we use that. And, yeah. Anyway, I encourage you to play a little bit with Jupyter so that tomorrow you are pros, and we can go and have some fun. Yeah. Oh, I should tell you that tomorrow I'll also introduce one more thing. So we're going to use Swan. Swan allows you to run Jupyter notebooks. But tomorrow I'll also give you another option, just so you don't think Swan is like the only thing out there. It's not. Just like there's many, like TensorFlow is not the only thing out there. Neither is Keras, despite of what you might have heard. It's good to know your options on the menu, right? So I'll tell you, there's another service called Binder, which works really, really well, and it's you don't have to have any account, anything like this. And it also allows you to run Jupyter notebooks, on somebody else's server. So you don't have to have your own Jupyter instance. So I'll give you both of those examples tomorrow. So Binder, Swan is a CERN version, let's say, a CERN Jupyter thing. And Binder is more of an open kind of thing, public. All right, so you You can ask me any questions, but I think we'll stop here today. Yeah. Thank you. Oh, question? Yep. Nope. It doesn't. It means more than that. But that's actually one of the things it means. It means deeper networks, right? It does mean that, but that's only one part of it. So, not the only part. But yeah. The one thing is to make a deep network. The other thing is to be able to train a deep network. And that's sort of where some of the other answers lie. You have to have some other there's other algorithmic changes, right? Both algorithmic changes and changes to how you train and how you learn that have been introduced to solve some of the issues that you otherwise have had before. So for example, the vanishing gradient problem has vanished now. So yeah. No, but that's something that works. So there are other ways. There's also other ways, but that's something that's a very fundamental idea, and that's basically a generally used idea in all of these. All variants of these networks use backpropagation. Yeah. So, but there are other ideas. Okay. Now, you can always, the C50, by the way, is I think is a fantastic thing. You can always get like an idea how well you're doing. Like your very first try costs you nothing, super quick, doesn't take any special data format, just dump your data in text and run it. It'll give you an idea how well you're going to do with boosted decision trees. Now those guys give you a pretty good benchmark. Now even if you're going to go and do your neural networks or convolutional neural networks over recurrent neural networks or whatever it is you're going to do, you always want to have a comparison point with something else. And that is a pretty decent point to look at. You can also try some of the others. Now, I should tell you about the software ecosystem. Maybe I'll use these last few minutes to talk about that. So there is, machine learning is a big field, right? So within that, you have tools for machine learning. And as a subset of that is the deep learning, right? So for example, TensorFlow is something more specific for deep learning, right? It's a framework which is built also to optimize on the low-level hardware, tensor operations, depending. Now why tensor? I guess there was, one of the speakers went into why tensors, but he didn't actually explain why you need tensors. The reason is that for neural networks, for just general neural networks, what you're doing is you can actually make a representation for all these computations that you're doing, for the derivatives and whatnot. You can represent them as matrices, right? They're matrices. So what you're doing is matrix algebra. You're multiplying matrices a whole bunch of times. Now, if you want to go to any higher, so remember, tensors are just higher dimensional matrices. And that's why, when you want to do something like, higher dimensional convolutions and things like that, then you're going to need higher dimensional matrices. And that means tensors. And that's why the whole thing is made to be optimized for tensors. And, so anyway, that's what TensorFlow and deep learning, the reason that sort of went in that direction. But you also have other things, like there are toolkits out there. For example, TMVA is one such toolkit that has a bunch of different methods together. So it means you can try boosted decision trees, random forests, neural networks, and compare how they all do versus each other on the same sort of problem. There's also another toolkit called Scikit-Learn. You might have heard that name mentioned already yesterday and today. And that's also one of those like multi-purpose toolkits. So it has pretty good implementation. It's a Python ecosystem, and it has very good implementations for tree-based methods and things like that. So if you're looking to use tree-based methods or some others, that's the way to go. And so this should give you a kind of a good overview of what the different things are. Okay. Good. Thank you, everybody. We'll see you tomorrow. Yeah.
repartir las constancias, ¿no? Ah, vas a conseguir todo como mañana, ¿no?
Bueno, van a repartir mañana.
Bueno, no, de una vez porque... Sí, sí. Así.
Ya las firmó
Pilar. Sí.
Sergey, dices, ¿no?
No, fue Pilar. Bueno, a ver, un momento por favor. Los que estaban ayer en la lista para las constancias, ya están listas. Ahorita las vamos a repartir. Y bueno, si usted venir mañana, pues continúa con TVMA, ¿sí? Entonces, sí, todas. ¿Cómo las hacemos? Pues me ayudan a repartirlas, ¿no? Porque es que no están en orden
¿Por qué no
alfabético.
los van nombrando? ¿Qué van a pasar?
Sí,